We're going to define quite a few terms in this lecture. That's typical for theory. In theory, you often set the stage, you define things, and then in that application you see how these things can be used. So in this one, we're going to define what we mean by a clique, by the neighborhood of a vertex, a component of a graph, a spanning tree of a graph, and a forest. Our first definition is that of a clique. You've probably heard this before, like in high school. The kids at school are so cliquish, meaning they belong to some kind of closed little subgroup. So that's exactly what we mean by a special kind of subgraph, which we call a clique. In particular, the definition is a subset S of the vertex set G is called a clique if every pair of vertices is joined by at least one edge, and if it's a simple graph, we mean by an edge. And any proper superset of S has this property. So what that means, simply, is it's a subgraph that's complete because every pair of vertices are joined, so it's a complete subgraph. And it's not contained in a bigger complete subgraph. So for instance, if it's a K3, it's not contained in a K4. Now, since you cannot add another edge in a simple graph, if the subgraph is complete, then it's easier to view what a clique is in terms of a simple graph. So we're only going to talk about cliques in view of simple graphs. So we're only going to talk about cliques like the graph on the right and not the multigraph on the left. Now, in the graph on the right, we can see a number of complete graphs on 3 vertices. Each triangle is a complete graph on 3 vertices. In addition, none of the triangles are contained in a K4. So each of these complete graphs on 3 vertices are a clique. So how many cliques does the graph on the right have? It has 4 cliques. We're going to define what we mean by the neighborhood of a vertex V. In order to define the neighborhood of a vertex V, first we're going to define the neighbor. And a neighbor of V is simply a vertex that is adjacent to V. So the neighborhood of V is the subgraph induced by the vertex set consisting of V and all its neighbors. Now, a lot of textbooks do not include the subgraph induced by all of the neighbors. They simply say it's the vertices of the neighbors of V. But our textbook also includes the edges that are induced by this vertex set. So again, the neighborhood of a vertex V is the subgraph induced by the vertex set V and all of its neighbors. So for example, in the graph below, to the far left, we have a vertex labeled U, and we want to see what is the neighborhood of U. Since U has degree 3, it has 3 neighbors. So we'll take U and its 3 neighbors and all the edges that are induced by those 4 vertices. So can you picture the neighborhood of U? Is that what you picture? You with its 3 neighbors. And it turns out in this example that all of the neighbors are adjacent. So the graph that we get is a K4. Our next definition is a component of a graph. Now we've just been looking at graphs that are connected for most of our examples. And if a graph is a connected graph, it has just one component. So let's see the formal definition. A component of a graph is a maximal connected subgraph. So that maximality says if you can add another vertex, if you have a vertex in the graph that's adjacent to at least one of these, it's part of the graph in consideration. So, like I said, if your graph is connected and you include this maximality, you're going to get the entire graph. So you only have more than one component when the graph is not connected. Now, for those of you who are familiar with an equivalence relation on a set, reachability is an equivalence relation on a set of vertices. An equivalence relation has to be reflexive, symmetric, and transitive. So, for example, if I can go from U to V, then I can clearly go from V to U. This is in a graph, not a graph. So it's symmetric. If I can go from U to V and V to W, then I can go from U to W. So there's the transitive. So reachability is an equivalence relation. And whenever you have an equivalence relation, you have equivalence classes. So it's kind of an interesting way to think of a component. A component, or the set of components, are simply the equivalence classes under reachability. So here's our familiar example that we've used several times. And we're going to look at it while we read the definition of the spanning tree. Now, a spanning tree is a subgraph that is also a spanning subgraph that is also a tree. So the subgraph induced by the blue edges is a spanning subgraph, since its vertex set is the entire set, and it is a tree since it is connected and has no cycles, so it is a spanning tree. So now let's look at proposition 2.1.2. A graph is connected if and only if it contains a spanning tree subgraph. So this is fairly easy to visualize. If it contains a spanning tree subgraph, that means it has a spanning tree. In other words, a tree that contains every vertex in the graph. So you can reach any vertex to, or travel from any vertex to any other vertex along the edges of the tree. So the graph must be connected. Let's look at proposition 2.1.2. Every acyclic subgraph of a connected graph is contained in at least one spanning tree. Now, it says every acyclic subgraph, so it has no cycles, but it doesn't say the subgraph is necessarily connected. So you have an acyclic subgraph of a connected graph, and so the edges of this subgraph are contained in at least one of the spanning trees. So what we've said so far, a connected graph has one component itself. And therefore, if it's not connected, it has more than one component. And each component has at least one spanning tree subgraph. And every subgraph that has no cycles is contained in a set of spanning trees. So we have one more definition. A forest. An acyclic graph is called a forest. Well, what's missing? An acyclic connected graph is a tree. So, since we're not saying it's connected here, it may very well not be connected. In other words, you would have a collection of trees. Isn't that cute? Collection of trees is called a forest. Okay. Any questions so far? So in conclusion, let's review our definitions. A clique is a complete subgraph that's not contained in a larger complete graph. So it's maximal in the sense of completeness. The neighborhood of a vertex is the set of all vertices adjacent to that vertex together with the graph it induces. A component of a graph is a maximal connected subgraph. Since it's maximal, that means if the graph is connected, it's the entire graph. A spanning tree is a subgraph whose vertex set is the entire vertex set, and it induces a graph that's a tree. And a forest is a collection of trees.